Today, I'll be discussing how we can utilize compressed sensing to directly visualize tomograms as data is dynamically collected, resulting in fully constructed volumes upon completion of experiment. The current tomography paradigm begins with the experiment, which takes hours, and after the data processing, which can also take hours or days. It would be beneficial to reconstruct the volume immediately when the data is collected, starting with the first projection and updating when more tilts are available. We show that this is possible with advanced compressed sensing algorithms. It can accommodate on-the-fly acquisition of new data as shown on the left. The volume quality improves as more projections are collected, and physical structure is visible as early as 33% of the experiment. These optimization-based approaches exceed at utilizing intermediate information to prove its overall quality with priori information. Within our framework, we have also developed the ability to accommodate changes to data tolerance as more projections are available. The stability and elasticity of dynamic CS allows us to adjust parameters, which can dramatically affect the quality of the reconstruction. Selection of the optimal parameter is often done with the guess and check method. Overestimating this parameter will produce blurred tomograms, while underestimating will retain all the noise in the output. These tolerance parameters can actually be tuned, and an accurate representation of the object can be achieved before all the data is collected. This means scientists can begin analyzing material systems throughout the experiment and accelerate the end-to-end process of materials investigation. Tomographic reconstruction algorithms are divided into two main categories: iterative and analytical-based methods. Analytical methods such as weighted back projection are computationally inexpensive, resulting in short construction times due to non-iterative nature and smaller number of operations. These methods require a lot of projections that contain a high signal-to-noise. Here, I reconstructed a cobalt diphosphate nanoparticle with mixed Gaussian and Poisson noise with 37 projections. You can see that reconstruction suffers from the lack of information as the structure is hidden by noise artifacts. Alternatively, iterative methods such as algebraic reconstruction technique are ideal for solving underdetermined systems as they produce regularized solutions to undersampled data. However, some speckle artifacts still remain in the reconstruction. Total variation minimization outperforms classical methods by reliably recovering the full structure and removing the speckle noise. On my 4-core computer, I was able to reconstruct this 1024 cube volume within the time shown above the volume renderings. However, these iterative techniques will quickly scale as they most likely need to run multiple times in order to determine optimal parameters. Thus, it would be beneficial to begin the reconstruction and interactively tune these parameters as the data is acquired on the microscope. Now let's look at this 2D synthetic image that was based from a real platinum carbon 3D tomogram, which can be used as a test object. We see that if we use traditional algorithms such as weighted back projection, the output suffers from missing information, while total variation minimization recovers key structure and fine platinum nanoparticles decorated on the surface. Compressed sensing can exploit prior information, where we assume the reconstruction should have high sparsity. That is, it should not contain a lot of variation, like the unnatural streaking we see in this traditional reconstruction. If we thus minimize the total variation, we can get a significantly better reconstruction using the same data. The benefits of total variation minimization become substantial when limited tilts are available. We can leverage the power of sparsity to regularize the early reconstruction when less than 50% of the tilt series is collected. This idea of leveraging sparsity was first introduced by Candice Romberg and Tao in 2004 and 2006. It was experimentally demonstrated by Paul Midgley and colleagues in 2011. We can also control the degree of uncertainty between our experimental data and reprojections with a tunable data tolerance parameter, epsilon. This means early within the experiment, a loose epsilon can be selected to suppress missing wedge artifacts and incrementally tightened as more information is available. Epsilon is directly coupled to the quality of the reconstruction and can determine whether the reconstruction could retain grainy noise artifacts or have a smooth, visually appealing tomogram. Here, I present the framework for our dynamic compressed sensing. To fully understand the properties of our algorithm, we use a synthetic strontium titanate nanocube decorated with gold nanoparticles as a test object. We are able to generate projections from plus or minus 75 degrees with 2-degree tilt increments, a range commonly acquired within the electron microscope. After every 2 minutes, a new projection is fed into the algorithm to simulate normal acquisition speeds for electron microscopists. We can observe that the root mean square error, or RMSE, descends downwards with a staircase-like pattern, indicating a new projection is available. The incorporation of new information continues to drive the RMSE down until the data converges early at about 75% of the experiment. We can see from the video on the right that fine structure is actually visible much earlier, and a fully constructed tomogram is available at the end of an experiment. Most importantly, 3D data interpretation can begin immediately after the first projection is collected. We can also directly compare our dynamic algorithm to a conventional reconstruction scheme, where the data processing occurs after all the data is collected. In the dynamic CS setting, we see that the RMSCs almost completely converge by the end of the experiment, while conventional CS needs an additional 30 minutes to an hour to become fully converged, increasing the total time to generate a tomogram. Overall, after the simulated experiment is complete, the two is indistinguishable. Both algorithms converge to the same solution. However, in reality, we won't be able to directly measure the object's error in an experimental setting, and we must assess convergence from the convergence, the behavior of the two terms in the cost function. First, the data distance, or the Euclidean distance between the reprojections and the experimental data. The goal of the algorithm is to keep this distance within a specified tolerance, epsilon, and once that constraint is met, the algorithm aims to minimize the object's TV. That precedes me to our second metric, total variation. Since this is a synthetic object, we can measure the original object's TV or TV naught. The algorithm is constantly trying to minimize its TV, and the addition of new projections perturbs the object to a higher state. However, our algorithm is able to correctly reweigh the relationship between these two terms to converge to each suitable metastable state. The success of these advanced algorithms is highly dependent on the selection of the data tolerance parameter, a process that is often determined by guess, checking, and resetting the computation. The tolerance is directly coupled to the quality of the input projections and can determine whether reconstruction could become over-smooth, losing high-frequency information, or too grainy, becoming hindered by noise artifacts. Here, I'm highlighting this effect on an atomic resolution iron-platinum nanoparticle collected by Meow collaborators. Poorly selecting the best tolerance will oversmooth the object, producing an amorphous blob, while selecting the optimal value produces a reconstruction where all the atomic columns are clearly resolved. This exemplifies the importance of getting epsilon correct. Compressed sensing has user-defined parameters which can dramatically affect the quality of the reconstruction. To alleviate the arduous process of determining the best epsilon, we have developed the ability to visualize intermediate results as users manipulate this tunable parameter. This means there is no need to reset the computation, and now the algorithm will use previous estimates to quickly explore new tolerances. The user can change epsilon as the reconstruction is running to make on-the-fly adjustments instead of waiting for the computation to complete. Tightening the tolerance produces a sharper tomogram, and we see internal voids within the STO volume become visible. However, over-tightening this parameter will retain noise structure from the previous projections, and the best value is highlighted in green. From the plots, we see the RMSC curve exhibits the same behavior as CD, as it consistently converges to its defined tolerance. This process is also symmetric, and starting from a loose estimate will so reliably return to the same solution. The user can turn the knob up or down to quickly and efficiently explore the parameter space and hone in on optimal values. The elasticity and stability of dynamic compressed sensing allows us to adjust this parameter, where the global solution for the cost function is purely dependent on the selection of epsilon. What I've shown today is dynamic compressed sensing can develop tomographic reconstructions in real time as projections are required. This means the volume can be visualized immediately when the data is collected, starting with the first projection and updating when more tilts are available, providing insight to specimen structure as early as 33% of the experiment. We've shown that this is possible in advanced compressed sensing algorithms, which accommodates on-the-fly acquisition of new data as the experiment proceeds and handles adjustments in data tolerance throughout the computation. This tunable parameter will help efficiently explore the parameter space throughout the experiment to ensure high-fidelity reconstructions are available upon completion of data acquisition. I would like to take a moment to thank my collaborators, Dr. Yi Jing, Huiho Zhang at our own National Lab, Marcus Hanwell at Kidware, and my advisor, Robert Houghton. I would also like to thank funding from the Department of Energy and Army Research Office. I'll be available in the chat to take any questions, and I'd like to thank you for your time.